video, we discuss some common applications of first-order circuits. First on our list are delay circuits. So these are circuits that create some delay uh, on its output in response to certain inputs. In this diagram, we have a series RC, and across the capacitor is a neon lamp. A neon lamp is a type of lamp that is open if the voltage across it is lower than its triggering voltage. Here, for example, it has a 70 volt triggering voltage. So once it reaches, so if it is not triggered, the neon lamp has a very high resistance because it is open. And once it triggers, it becomes a very low resistance load. Once it triggers, however, and we decrease the voltage, it continues to be in the on state until it reaches another voltage level that is low enough that it turns off. So when the switch is turned on here, the capacitor will charge. So initially, the capacitor has no charge, and therefore the voltage is zero. And once it is charging, the voltage increases until so it increases at the rate that is proportional to this quantity. And once it reaches the triggering voltage of the neon lamp, that neon lamp will trigger. Okay, so once VC reaches the trigger voltage, the neon lamp fires, and uh, immediately after that, the capacitor will start to discharge. Okay. But the neon lamp, even it is below its triggering voltage, will continue to be in the on state. And until the capacitor voltage is low enough that the lamp turns off. Once the neon lamp turns off, the capacitor charges again and the voltage across it rises and the cycle repeats. This repeating scenario will create a blinking neon lamp with a blinking rate depending on the time constant, which is given by this quantity. Thus, we can vary that rate by varying the time constant tau. And in this diagram, that can be accomplished by varying the value of R sub 2. So let's have an example. So here we have a circuit utilizing a neon lamp where R sub 1 is 4 mega ohms. And initially, let's make R sub 2 equals to 0. The neon lamp has a trigger voltage of 70 volts and it turns off at 30 volts. So the resistance of the lamp is assumed to be at 200 ohms when it is turned on and infinitely large when it is off. So the question is, how long does the lamp turn on the first time the source is switched on? And on the succeeding cycles, how long does the lamp turn on? Okay. So the first time that we turn on the switch, so take note that the capacitor has no initial voltage. The voltage V sub C of the capacitor will build up until the trigger voltage is reached. Now, the time it takes to reach the trigger voltage can be found by using the formula for the series RC. Take note that even though the neon lamp is connected across the capacitor, initially this is an open circuit, so therefore we have a series RC. Therefore, we can use this formula now to find the time it takes to reach 70 volts. We can substitute V sub C for 70 volts and compute for the time. So let's do that. And solving for time t, and that should give us a time of zero point 0.4 seconds. So initially, the time it takes for the capacitor to reach uh, 70 volts with an initial voltage of 0 is zero point 0.4 seconds. When the neon fires, the circuit will now look like this. So it becomes a low resistance element with a resistance equals to 200 ohms. And at this point, the capacitor will discharge to that low resistance element. Now we can convert this circuit into a circuit that looks like this. So we convert the circuit around the capacitor into its Thevenin's equivalent, and that will give us a very small voltage, almost zero, and a series resistance that is almost the same as the resistance of the neon lamp. So here we can assume that it is a series RC, but it has no voltage. But the capacitor has a voltage that is 70 volts, which was um, reached when the neon lamp fired. So at this point, the capacitor will discharge to the 200 ohms until the voltage across it becomes 30 volts, at which point the neon lamp will open. Now, how much time is needed to discharge the capacitor to 30 volts can be found again by using the formula for series RC. And this time we substitute the value of 30 volts to this voltage, which is the voltage of the capacitor. V sub S is 0 because this has no uh, voltage. But here we now have an initial voltage which is 70 volts. So computing for the time, that will give us 16.9 microseconds. So this is the time required for the capacitor to discharge from 70 volts to 30 volts. Now, once the neon lamp turns off, the capacitor again will charge up to 70 volts, which is the trigger voltage of the neon lamp. But note that this time the capacitor has an initial voltage of 30 volts. We can use the formula for series RC by letting the voltage equals to 70, but this time we have an initial voltage of 30, and that should give us a time of 0.277 seconds. So this is the time required for the capacitor to reach 70 volts at an initial voltage of 30 volts. If we sketch the waveform across the capacitor, the voltage waveform, that should give us this sketch. So initially it starts 0 and it rises to 70 here. Um, with a time of 0.4 seconds. And then the neon lamp fires, it discharges from 70 to 30 in just 16.9 microseconds. And upon reaching 30 volts, the neon lamp opens. The capacitor again charges up to 70 volts uh, in 0.277 seconds. Okay, and the cycle repeats. So initially, the charging time for the capacitor is slightly longer compared to the succeeding time, which is only 0.277 seconds. Another popular application of first order circuits are in relay networks. So these are circuits that uses relays that are simply electromagnetic devices used to operate switches to control another circuit. So here we have a simple construction of a relay. So it consists of a core made of ferromagnetic material, and around that core is a coil with sufficient number of turns. We also have a rocker and a hinge that is a movable element that moves about the hinge. We also have contacts. So this one and this one are contacts. So normally the coil is connected to a source through a switch. Okay, so when the switch closes, a current will flow through the coil, and that coil will produce a magnetic field that will magnetize the core. That is, the core becomes a magnet. And if the core is strong enough, the magnet created on the core is strong enough, it will start to move the rocker. So this part here is attracted to the core, and this part here will move in that direction. And this contact on the left will start to touch the contact on the right. Okay, so this part here is normally connected to another circuit. So let's say we have another source and a resistance. So if these two contacts here will touch each other, it will create a complete circuit that will allow current to flow through this resistance. Okay, we have another simple illustration here of the relay. So along with the external circuits, so here the coil is connected to the source with the switch S1, and the contacts represented by S sub 2 is connected to the load R. So let's say we have a source here. Okay. Let's call this V sub 2. So when S1 closes, current will flow, the core becomes magnetized, and if it is strong enough, the switch will start to move. Okay, so S2 here represents the rocker, and if S2 closes, current will start to flow through this part here. Now, this circuit here is actually a series combination of the source and the coil, but the coil can be represented by an inductance in series with a resistance. So therefore, this part here is really a series RL circuit. So let's have an example of relay circuits. So we have a relay that has a resistance of 200 ohms, an inductance of 500 millihenries. and it is stated that the relay contacts closes when the current in the coil reaches 350 milliamps. So when the switch closes, the contacts does not immediately uh, closes because the current through the uh, coil will have to build up. So take note that the current, so this is the current here, so this is BS, so this is the current, will build up in this manner. Okay, so once it reaches a certain value, so in this problem it is 350 milliamps, the magnet created in the core will be strong enough to move the contacts. So that is what is meant by this uh, statement here. So the question is uh, the time required or the time that will elapse between the application of the 110 volts to the coil and the closure of the switch. Okay, so since the coil looks like a series RL, the complete response is given by this equation where tau there is the time constant of the series RL, and that can be computed. So since the contact closes at 350 milliamps, we can substitute that value here for I and then compute for the time that current becomes this one. So that will give us uh, this answer here. So it's 2.5 milliseconds. Well, that is fast enough, although not uh, that immediate. That is, if I apply the 110 volts, the switch, uh, the contacts immediately uh, close. Okay, so there is a little time delay, and that delay is given by this. Another application of first-order circuits are in integrator circuits. Here we take an input and the integrator circuit outputs the integral of the input. So an integrator is an op-amp circuit uh, in which the output is proportional to the integral of the input. So the feedback resistance, so remember our previous discussions in op-amps where we have here a feedback resistance. So we replace this resistance by a capacitor in order to achieve the integral function. Since we're talking about ideal op-amps, so the current through the inverting and non-inverting terminals are both zero, and since this part here is tied to the ground, that makes this part here also 0 volts. Um, so by writing KCL on this node, we get this equation that is the current to the resistance is equal to the current to the capacitor. Now we can write the current to the resistance using Ohm's law. So this is V sub I. So this is actually V sub I minus 0 here. Okay, there's a minus 0 there, divided by R. And since we know that for a capacitor, so take note again that if this is I and this is V here, we have I equals. So we apply that relationship So the voltage across the capacitor is 0 minus V naught. Okay, so this is the voltage, and we can write it in a more simple equation that looks like that. And from here, we can compute for the output by using integration, but we need to introduce a constant. So this is the initial voltage across the capacitor. If we assume that voltage to be zero, that means the output is this one, which is really proportional to the uh, integral of the input. And it is interesting to note that it is also the reverse because of the negative sign. So let's have an example to see the integrator in action. So here we have an input voltage that is a cosine function, and we have R and C here. So determine the output voltage of the integrator assuming the capacitor is initially discharged or the voltage is zero. So we can use the formula. So we just substitute and that will give us this one. So the output is a sine function as expected because it is an integrator. In our original design of the integrator, it is noted that the output is not really the integral of the input because of the constant that is equals to the negative of 1 over RC. So in this example, we want to know what are the changes that is required so that the circuit will really output the integral of the input. So the formula there, this one is this one. And to get rid of the RC, the first step would be to make RC equals 1. So that means that C must be equals to 1 over R numerically. And that will give us this one, this result. However, the result is not still the integral of the input because of the presence of the negative sign. We can get rid of that by passing the output of the integrator that has a C that is equals to the reciprocal of R to an inverting amplifier which has an input resistance and a feedback resistance that are equal. So this will be the final design. Okay, so this is the integrator and this is the inverter. So in the integrator, C is equals to 1 over R, and that should give us an output that will look like this. Then we pass this output to an inverting amplifier that has these values that are equal, and that should give us a perfect result, which is the integral of the input. Another application of the first order circuits are in differentiators. Here we also use a an op amp, but instead of using a resistance here, we replace that by a capacitor. And so the output of the differentiator will be proportional to the derivative of the input. So here again, we note that This is tied to the ground, therefore this is 0 volts. The current through the input terminals are 0, and we can say that this current is equals to this current. Okay, but we can replace I sub C by C dV dt, and the voltage across the resistance is this is 0 minus B naught divided by R. That gives us the current, and we can compute for the output as this one. Okay, so it is the output is not really the derivative of the input, but it is minus RC times the derivative of the input. So let's have an example for the differentiator. Here we have an input which is shown as a waveform. So this is a triangular waveform. And we are required to sketch the output. Okay, so we know the output to be equals to this one. So our first focus would be to first compute for this. So doing that will give us this answer for the output. So this part here would be in seconds because the product of RC is in seconds. So the output is really this constant here times the slope of the waveform. But the slope of the waveform is different depending on which time are you in. So we need to compute for the slope on different times. For example, the slope between 0 and 1 is this one, and that slope is also this slope between 3 and 4 milliseconds. So we might as well compute for that slope first, and if we do that, that will give us the slope here. Okay, so the slope here is using the traditional method of computing for the slope, which is rise over run. So the rise here is 10 minus the 0 divided by the run, which is 1 minus the 0, and that should give us 10,000 volts per second. Then applying this here, that should give us an output which is negative 2 volts. Now for the time between 1 and 3 milliseconds, the slope is this one. So the rise there is negative 10 minus 10, and the run is 3 minus 1. Okay? And that should give us a negative 10,000 volts per second. And computing for the output, that should give us a positive 2 volts. Hence, the answer would look like this. So between 0 and 1 millisecond, it is negative 2 volts. Between 1 and 3, it is positive 2 volts. And between 3 and 4 milliseconds, it goes back to negative 2